Welcome to Math 252. I'm talking about problem number 23 from section 5.1 of the Hughes-Howett text, where we've got a car that's going 50 feet per second and it's braking at a constant rate. 5 seconds after it starts slowing down, it comes to a stop. We're supposed to graph the velocity function from t equals 0 to t equals 5, so for the first 5 seconds. We're supposed to figure out how far the car travels, and then we're supposed to find out how far the car travels if we double the initial velocity, but the braking rate is still the same constant rate. So in order to work this problem, we're going to need some basic facts. One big one from this section and some that you already know. The big one from this section is that if the velocity function is positive, the total distance traveled is the area under the velocity curve. So if we want to find the total distance traveled from the time we start slowing down to when we've come to a stop, all we need to do is find the velocity curve, graph it, and integrate it, find the area underneath it from t equals 0 to t equals 5. You also got to remember that if the derivative of a function is a constant number, then that function must be a line. So we've been told that the derivative of the velocity, that's the rate at which we're losing velocity, is a constant function. So in fact, we know that this velocity function must be a line. And we can even figure out the slope of that line, which I'll need in part C. We're losing 50 feet per second in 5 seconds, so we must be decelerating, losing velocity at the rate of negative 10 feet per second, or negative 10 feet per second squared. So let's put these pieces together. Let's take a look at parts A and B. Here we got a graph of the velocity as a function of time. We've got 2 points on this line. We know that when t is equal to 0, we're moving at 50 feet a second. We know when t is equal to 5, we're not moving at all. And so we can draw a line between the 2 points. The solution to part B is the shaded area under the line. The area, which we don't even need calculus to figure, it's a triangle. So you take the base times the height, take 1/2 of that, and you get 125 feet. Now, for part C, we're going to be decelerating at the same rate. So we're going to be moving at 100 feet per second. It's going to take us 10 seconds to come to a stop. Here's that graph, which looks a lot like the previous one, except now we're starting at 100 feet per second and it's taking us 10 seconds to come to a stop. The distance traveled again is the shaded area, the area of the triangle, and we get 500 feet. Now, it's easy to see that doubling the initial velocity makes the distance traveled while you're coming to a stop, 4 times as large. Here I've put our 2 graphs together. I've got the first graph in the lower left, and above it you see the graph of the second velocity. And it's easy to see from this picture that the area underneath the second curve is going to be 4 times the area underneath the first curve. And in fact, it doesn't really matter what the numbers were. Whenever you double the velocity, it's going to take you 4 times as long to stop if you're decelerating at a constant rate.